Hello and welcome to the New York City Category Theory Seminar. Today, for the second time, we're having Charlotte Aten speak. She spoke last year. She's at the University of Colorado at Boulder, and she's going to talk about invariants of structures. Take it away, Charlotte.
Well, thank you so much for having me again. I'm happy to be here talking about something that's actually a little bit older. This is part of my PhD thesis work, and well, today I'll be discussing, I guess, what is maybe most truly my pandemic result. Although I did a couple of things during that time, as I'm sure most people did. Uh, so before I really get started, I will just give you an outline of what I'm going to do. Um, I'm getting a little bit older now, and I know I'm not old yet, but I'm getting older, and I am starting to realize that starting off with examples is really the way to go. We all have the impulse of wanting to give the complete abstract nonsense first, but I'm going to give you a couple examples that motivated this project, and then I'll talk about the historical connection with Bourbaki's notion of structures. And then I'll summarize my thesis results and then give you the gory details to the extent that time allows. So, yeah, that'll be what I'll discuss. And so, first, I want to talk about associating certain polynomials to undirected graphs. So, in other words, oh, can people see my mouse going around here? Can I at least point to
Perfect,
things?
perfect, perfect. We see it. I
Okay.
see it.
Yeah. So if I have some set of elements and things A1 through AN, A choose 2 would be the set of all unordered pairs, in the usual way. And so for each unordered pair, I could have a variable xij. And by this definition, I suppose xij and xji are supposed to be like the same variable. We won't worry too much about it. And so if I have some graph, so I'm using the model theoretic notation where I have this bold G and it has some universe A that is that set of vertices. And for reasons that will make it clear, that are more systematic later, I'm going to call the edge relation little f, but it's just some set of those unordered pairs. And we could evaluate one of these variables on G by making it the indicator function of that edge in the set of edges F. So if G has an edge between the vertices AI and AJ, then this quantity would be 1, and otherwise it would be 0. So we could do that if we wanted to. And then we would be able to extend that, in the natural way in order to form monomials. Like for instance, maybe this x12, x23, x31. And so I could apply this to the graph G, some particular graph G, by having each of the xij uh, act on G as that indicator function, and then multiplying the result. And so the effect that that would have is that, well, if there's an edge between each of those, the three corresponding vertices, A1, A2, and A3, then the product would be 1, and we would get, a 1 when we have a clique with those three vertices in the graph G, and otherwise we'd get a 0. And so we can do the same, well, okay, I guess before I say that, so this property is not really like a very natural property in the sense that it's not invariant under renaming the vertices. Like, in other words, this is really checking for those three specific vertices, A1, A2, and A3, sort of a more natural property. That you might think of as truly a graph property, is something like just having a triangle in general, because that's something which is not, changed by looking at a different isomorphic copy of the same structure. Uh, we usually don't really think of something that depends on the specific presentation, the specific instance in the isomorphism class as being a property of the thing, right? So, what is a property is just having a triangle in general. And we can actually think of that as corresponding to this polynomial where I'm just summing those type of monomials that I did before for A1, A2, and A3, but I'm summing them over all possible triples of distinct vertices. And so if I do that, then the effect that this polynomial P has on the graph is just giving us the number of triangles in G, because we'll pick up a one for each term that has such a triangle, and we'll add them up. So uh, now I'm going to make a somewhat big and vague claim, which is that every property of finite structures can, in a sense that I'll make more clear later on, and that you can check my thesis for more details or the corresponding preprint. But I claim that every property, in some sense, of finite structures can be computed by evaluating at such polynomials. And so I have to now, explain to you in better detail what I mean by that, because of course, we could cheat and just make like, you know, maybe I want to invent like a variable that just checks whether or not the property holds in a structure. That's a kind of a cheap way of, thinking that we have a polynomial that computes the thing, right? We want something that's more interesting, and I claim that I have something that's more interesting than that. Um, okay. So my one other example is of associativity. And actually, this was the original context in which I noticed this. I won't give all of the reasons why I was thinking about this exact thing, but this is the original way that I noticed this phenomenon that I ended up being able to prove happens in quite a bit of generality. So if we play the same game where we have some universe, some finite universe, uh, well, we could make variables instead of for unordered pairs, we could make variables for ordered triples. So things in A cubed. And if we have some ternary relational structure, a set equipped with some ternary relation, which I'll also call little f, then we can evaluate, oh, this is supposed to be xijk. So imagine if I actually had the annotation menu that I would rewrite that as a k, ijk. We can evaluate that on the structure A in the same way. It's the indicator function of that specific triple, ai, aj, ak, in the relation F. All right, well, uh, let's just assume that the ternary structure is a magma in the sense that we take ai, aj, ak in the relation F to mean that abusively that there is a binary operation F that when you plug in AI, AJ, you get AK. Well, then we can express associativity given that assumption that we know we have a binary operation in terms of the XIJK in some polynomials, in terms of some polynomials in the XIJK. And so if you've seen like writing down the equations that define the variety of associative algebras, like n-dimensional associative algebras, then this is going to look pretty familiar because these are like the structure constants. Well, if you're going to have that this triple associates, AI, AJ, AK associates, and the resulting product is AL, then you need exactly one witness to these two formulas here. So you need something that is the product of AI and AJ that in turn you combine it with AK and you get AL. But on the other hand, you need some potentially different thing, which is what you would get when you combine AJ and AK under F. And then that AI combined with that gives you AL. So you would need exactly one witness to both of these formulas.
So now in here, you haven't, you said in words about it being the graph of an operation, but you've only put the uniqueness condition when you wrote your associativity, as opposed to saying the third thing is uniquely determined by the first two.
Yeah, so I'm using the fact that this would be true if I knew that I had an actual binary operation as opposed to just some ternary relation. But I'm just gonna give what the formula would be under that assumption, but I'm not really enforcing it in any of the expressions that I've given here.
Okay, thank you. I just wanted to get that clear.
Yeah, absolutely. Like this is this is going to mean something different if you are just allowing a general ternary relation. Yeah, so you would have to be more careful, but originally what I was interested in was just this, so this will be enough for now. But yeah, absolutely.
Are you capable of talking about partial operations like in a finite field?
Well, I mean, this I mean, this type of thing, I guess I'll give you a definition of what I mean by finite structure a little bit later on, but pretty much anything you intuitively think of as a finite structure can be construed as such an object. And then the question the more interesting question is like, is there a presentation in terms of this framework that will turn an interesting question that you have into something that's like a non-trivial kind of calculation with these polynomials? So there are many ways of construing just basically anything that you would think of as a finite structure into such a setting is what I'll describe in more generality later. But so certainly finite fields are doable. Like any kinds of structures in finite fields are doable. The question is just can you choose the language correctly so that it gives you interesting calculations about your object.
So you're getting not only algebraic theories, but essentially algebraic theories.
Um, it's possible to do. So I don't actually know the relationship between so maybe the thing to look at would be like what's like locally presentable categories, but I'm still not too familiar with that yet. I just had this specific motivation, so I did this specific thing. But you can get things that are not algebraic. Like you can get like topological spaces and things that don't have the nice structure of algebraic categories this way.
Oh wow. Okay, good. Very nice.
Yeah.
Go on.
All right. So, yeah. So I wish I knew the relationship between this and the notion of like something that's locally presentable, but I don't know the relationship yet. Um, okay. So anyway, if we assume that we have a binary operation, we want exactly one witness to both of these formulas. So these terms would correspond to two polynomials, which, as I mentioned before, are like the polynomials that you would get if you were looking at the equations defining the algebraic variety or algebraic set that it's like the moduli space of associative real algebras. So we would want to have each of these things come out to one on a given structure. And so one way to enforce all possible instances of this to come out, or sorry, we'd want the difference of these to be zero. So each of these would come out to be one. We want to force each of sums of these differences to be zero. Um, and so one way to do that is like this, since we're assuming that everything's real. Uh, and so if you evaluate on your structure, you want this to be true. That's equivalent to associativity under the assumption that you have a ternary relational structure. And again, this is the moduli space thing that you would do for real algebras. And so, okay, so we would want that. And so I'm interested then in this polynomial. And if you decompose it by looking at the different cases where, like, say, I, J, K, and L are all the same, or maybe the I, J, and K are the same, but they're distinct from L. If you look at all these different cases, well, you'll see that the sum, breaks down into these cases. And if I just pick off the first one, I'm going to look at that in a little more detail. And I see that this term is really just counting the number of times that you have just the same element associates with itself, and it actually gives you itself back in the end. So uh, this isn't really counting the number of a substructure inside of our original structure because it's counting the number of times, sorry, that this fails to occur. It's counting that because you'll pick up a one if you don't, if you don't end up getting a witness for both of these. So that's still not quite counting substructures, but I claim that if you actually square this and expand it out, it will break up into smaller pieces, which are actually the counts of certain substructures. I just didn't fully expand it because it becomes quite involved to actually look at all the pieces. I've used the computer to do it before, at least for small, like, for like three elements, maybe four elements. But it's it's a bit to write out. But what I noticed was that it looked like it was breaking up into this polynomial in terms of these counts that were these counts of these certain small substructures that were like witnesses or obstructions to the desired property occurring. And so that was actually the original thing that motivated me to go in this direction. So, well, that was the motivation, and I gave a sort of a more down-to-earth example with graphs. And so now I have to argue too that this type of phenomenon where the thing I want to check can be represented as some kind of polynomial, and then I can decompose it into these nice pieces, that happens in quite a bit of generality. So I'm going to go way back. Well, not way, way back, but back to the 20th century. And so in writing The Elements of Mathematics, Bourbaki sought to set out this systematic description of all the mathematical structures that would appear in the whole textbook series, And so, Bourbaki was very, systematic, and they wanted to have like a really good overarching framework for everything that was going to happen throughout the rest of the series. So you would learn this abstract definition of structure, and then you would take it with you throughout the rest of the textbooks. And every time you encountered like a group or a topological space or a graph or whatever, then you would say, these are, this is some kind of structure. It's just some kind of structure. And you would already know a bunch of basic facts about such things. So I came across this kind of idea, and then I ended up finding that Bourbaki had described something similar. And so this is my take on basically what they were saying. If you actually go to read it, it is presented in a way that's more involved in this. But basically, they said that you would want to have a set and a bunch of basic relations, similar to what people now do in model theory. But their relations were they were a bit more liberal with what constituted a relation. And so if I'm using this SB for the power set, for the set of all subsets of a set. And so their notion of relation allowed arbitrary finite compositions of products and power sets of the underlying set. So for instance, the product of the set with the power set of the product of the power set with some Cartesian power, and so on and so forth. So they allowed something like this, but it was just products and power sets, presumably because they wanted algebraic stuff and they wanted topological stuff, and that looked like that was enough. If you could just do arbitrary combinations, you could do anything that they were interested in thinking about. So, and then, they defined what we would now call morphisms, and they proved a bunch of results about them, which we would basically now consider to belong to category theory. So once Eilenberg and MacLane had actually established this as an area, Grothendieck and then Cartier were asked to produce a category theory component for the elements. Although if either of them did, they never put it into the textbook.
Also, by the way, MacLane's autobiography has an interesting account of his trying to influence the Bourbaki people about category theory and structures.
Oh, thank you. I haven't seen that actually. Yeah, that sounds really neat. Yeah, I got to check that out now. So, okay, so there were discussions in the 50s that seemed to indicate that they basically felt that the elements would have to be rewritten in order to accommodate the new notions from category theory. And it also seemed like it was going to be hard to reconcile the structural and categorical viewpoints together to have like a coherent foundation. So they just ended up deciding not to do it, which, was maybe, that was when people complain or criticize the viewpoint in this textbook series, like this is kind of a really damning thing, right? That they had this like big overarching abstract formulation, and then they decided that they found a better one, couldn't reconcile it, but that also didn't really affect the rest of the series, even though ostensibly the whole thing should have been based on it. But I mean, I don't have strong feelings either way, I guess, but that was that was what happened.
Can I just say over something from my thesis advisor, Alex Heller, who was a student of Eilenberg, and he said that Eilenberg told him, and again, I don't know if this is historically whatever, but he told him that Bourbaki couldn't deal with homological algebra because objects were defined only up to homotopy, and that was against this idea of what a structure is. A structure is a set of things. It's not an equivalence class of homotopy, similar things.
That's an interesting point. And it also actually makes me think that this was kind of a departure from what was common in algebra prior to this, where now we don't do this, but it used to be the case that an algebraic structure by definition was a set with operations and an equivalence relation with which the operations were compatible. And now we just tend to talk about things like, well, there is a quotient structure, and maybe that's, nicer than the original thing that's defined strictly and not up to representatives. But we don't talk that way anymore. But actually, it was quite common to talk like that back at the beginning of the 20th century. So it may be even strange that they decided not to allow that sort of that wiggliness up to equivalence.
Right, right. Anyway, Heller said they couldn't talk about a projective resolution of a module. They couldn't deal with that because of this. Anyways, I don't know. Anyways,
Yeah.
go on. Very nice.
All right. Thanks. Um, that's interesting as well. So in my thesis, I presented one possible categorical notion that corresponds to Bourbaki's concept of structure. And so the main result is a generalization of the result of Hilbert on symmetric polynomials, and this just generalizes to finite structures. The Hilbert result is for just sets. So whatever Hilbert's result on the elementary symmetric polynomials generating the algebra of all polynomials, that's in this setting, that's the result just for sets with no additional structure. There's some kind of chat. Oh yeah, I also think the comments have been very interesting. Thank you. Um, so
Actually, now that you mentioned this first bullet point here, I'm wondering if this is going back to the previous slide, the last comment about Bourbaki not being able to reconcile their viewpoint with the categorical one. Are you saying that your thesis, in some sense, tries to give a potential um, answer to this? Is that what it's saying?
yeah, so that's what I'm saying, is that this is one potential answer to that. I mean, it might not, I don't know if they would have accepted it as a synthesis, but it I mean, even though I've done this and I think that it's interesting and it was part of my thesis, I would probably not open a textbook series with this definition as the definition of mathematical structure, which you must understand before knowing about groups or spaces. That doesn't seem like the way to go. So if they would accept this, I still think it might have been reasonable for them to just completely give up on trying to present it in their textbook series. Um, but yeah, and I'm not claiming this is the only thing. I mean, they might have not even said this is a good answer. I don't know, but this is maybe an answer to what that synthesis would have looked like or would look like. Um, okay, so yeah, so and as I mentioned before, this generalization ends up telling us that in some sense we can check properties by counting small substructures. And there's a bit of an asterisk on the small, but I'll mention that later. So this actually ended up being an appendix to my thesis because I just kind of gave the presentation that was in terms of like more familiar finite relational structures for model theory. And then I said in the appendix, you can actually do all of these proofs exactly the same in this more general setting. So if you don't want to, if you didn't want to read the categorification of it, you didn't have to, but all of the proofs are the same proof. So I also showed that there's an embedding, I have an embedding result that you can use the Unit lemma to show that actually categories of structures that are built from sets can actually be viewed as classical model theoretic relational structures. That doesn't play super nice with this result though, because of the Oneda embedding, you generally end up with something that's like has an infinite amount of basic relations when the original thing only had finitely many. So this doesn't it doesn't completely trivialize, I guess. You can think of everything made from sets as a model theoretic relational thing if you allow an infinite number of basic or like a proper class of basic relations, which is a bit much, I guess. All right. Well, let me define structures for you. So um, if we have some index category, which we usually are just going to think of as a discrete category to start out with, and two categories C and D, I'm going to call a functor from that index category to the corresponding functor category a presignature. And as you might guess, this isn't good enough to be a signature for a structure. Which is supposed to tell us the arities of the basic relations. So yeah, I'll have to do a little bit more. But in the examples for graphs and magmas or ternary relational structures, the index category was just a trivial category with one object, and C and D were set. And so in the graph case, I'm just thinking of rho applied to the one object that's in the trivial category would be the functor that takes a set to, A choose 2. And similarly, the one for the ternary relational structures would be the one that takes the set to its cube.
Mhm.
And you can, of course, extend maps between sets in the appropriate way in each of those cases.
How are we supposed to think about C and D? What are C?
So, so for instance, okay, so in these cases, they're both just set, right? But
Right.
In general, you can think of, and you'll see as I go through the rest of the definition, you can think of C as giving us it's sort of like that's where the universe comes from. That's where the underlying object, underlying set, or underlying space, or whatever comes from. D is like where the basic relations of the thing live. So, for instance, I might have an underlying set, but I want to make a group or a space from that somehow functorially. And so then my basic relations will somehow be inside of that group or space or whatever it is. And then I called it the index category. That's supposed to index our basic relations. So if it's just a discrete category, we think of that as like a set of basic relations, but we could also have morphisms that would represent some additional structure that has to hold between those relations.
Just to make sure I understand, the reason it was I had only one element there was because you only had one type of thing, such as graphs in one case and the relations in the other.
Yeah, but if I wanted to have like 6 different basic relations, each of with a different type, one's an unordered graph, one's a ternary relation or whatever, then I would have maybe a 6-object discrete category instead.
And you could have morphisms between the sorts. In other words, I is the sorts, and you could have morphisms between the sorts.
Yeah.
So it gets really complicated.
Yeah, so you can enforce symmetry on individual sorts, or you can force them to have some type of relationship with each other as well. And so I call those the individual sorts are like the relations, and the things that go between them are like relators. But yeah. So, well,
Oh, sorry. Do you mind if I ask? I want to see if I'm understanding this. So, is another example for like topological spaces to take like a functor sending a space to a particular to like this subset of open sets if X is viewed as a topological space? Like,
so you're saying like if C is top and D is set, then like taking the space,
yeah,
the set of open set. Yeah, I mean, you could do that, for instance.
I see.
And then you could ask like, to each for each underlying space, I'd have like a basic relation, which is a sub collection of all open sets on the space, for instance.
I see. Okay, cool. Thank you.
Yeah, of course. And of course, if you want to make spaces themselves, you could take C and D to both be set and do the power set functor, and then you could have collections of subsets of the underlying set. So, okay, how do we actually get the structure that we want to have a nice category of these things? So I'm going to associate to each pre-signature an extractor, which is a functor that is, so it was I goes to functors from C to D. This is the thing that you would guess that it is, where, if I fix a C, then I obtain a functor from I to D. And so that corresponding functor. And I'm thinking of its argument as like a subscript to rho. So the value of that at a particular object would be a functor from the index to the target category. And so you can think of this as like, the like in the cases that we saw before, like for graphs, this would just be taking the trivial category to A choose 2 for graphs, or it would be taking the trivial category, the single object in the trivial category to A cubed, the set of all triples. This is like all the stuff that you get out that you're going to make a relation by taking sub things of it.
So,
Uh,
excuse me, is that mu sort of a currying or an adjoint to the map from I to the functors from C to D?
So that's a very reasonable question to ask, and I actually have not thought too hard about the answer because back when I was doing this, I definitely had wondered, similar to the discussion about like locally presentable categories before, I definitely wondered if there was like a more abstract way to formulate this, but I actually just wanted to prove the combinatorial, I mean categorical, but combinatorial result. So I have actually not thought too much about this, but this seems to be a very natural thing that you can do. So I would imagine that, yeah, it probably is the currying in the appropriate, if you appropriately set up the notion of what an exponential object in the category of categories is, and you have a good definition for that, then I would guess that that's probably what it is. All right.
Thank you. Thank you. Thank
Yeah,
you.
yeah, of course. Um, so a signature, unfortunately, this definition doesn't work to give you the definition of a category the way you would want it to. I'm not 100% sure about this connection, but I think that when Bourbaki talks about transportable relations, I'm not 100%, so don't quote me, but I think that they observed like some similar phenomenon that like you in general won't be able to like take a function between the underlying universes of two structures and get it to like actually produce a substructure of the codomain from the domain. So like what you would guess would be a category of these things just doesn't exist in most cases. This doesn't have enough structure. The pre-signatures don't have enough structure to give you a category of structures. So uh, we need to be able to take images in a certain sense in order to make all of this make sense. So a signature is, the pre-signatures that have the good property. And so this good property is that if you have a monomorphism of this extraction at some object A, uh, so this is kind of what you would think of as being a structure. Like this would basically give you like a subset of A choose 2 for the graph case, like a graph, a set of unordered pairs, right? That tell you which edges are there. Or in the ternary relational structure case, this would be giving you a subcollection of the triples from A cubed. And so what you would like is that if you have a map from A to B, that you are able to actually produce the corresponding substructure or structure on B that comes from applying that function to the things in from A. And so in general, that doesn't exist. But if you have that the image of this composite of this extraction functor or this curried thing at H composed with the monomorphism F that's like representing your subobject. If that exists in all possible cases, then I'm going to say that that functor rho is a signature. These are the ones that do the thing that you would expect. In other words, you can move things forward through function or through morphisms from the original category C. So like, you can take images in the sense that you would expect to be able to.
Do you mind if I ask again about this topological space example? Actually, going with what you were saying, which is if I look at it from set to set and I take the set to its power set, would
Yeah.
like the choice of such an F give me like a specific topology on that space?
So
And
what I said there was actually weaker than a topology because so I think I actually called it like a I don't know pseudo topology or something. I mean, in general, you would just have a collection of subsets of the power set or a collection of you'd have a subset of the power set, right? So just a collection of things that are the data that you would want for open sets, but they don't necessarily satisfy the conditions. So there would be a subcategory of the category of such structures that would be topological spaces, the ones for which the axioms hold. But this doesn't, that what I mentioned before doesn't enforce that in any way. So, or if you want to think of it this way, what that really is the category of hypergraphs, if you want to say it that way, and topological spaces are like special kinds of hypergraphs.
okay, cool, thank you.
Yeah. So, in nice examples where we just have a discrete category for our index, just a list of basic relations, and that target category D has all possible images, then this always happens for any pre-signature in that case is going to be a signature. But in general, you can't expect that. It's more complicated in general to determine whether or not this is the case that you have a signature. All right, but we do have examples. And so a structure of a given signature is, well, you take some object that's your underlying universe, and we're going to refer to a sub-object, which I'll call bold A, of that extraction functor in that functor category from I to D. I'm going to say that that's a structure of signature row on the object A. And so that's a purely categorical definition that doesn't use, anything specific about what types of relations we're allowing. So I don't know if Bourbaki would have accepted this, but this is a definition anyway. So, okay, now we can start playing all the games that we would, with classical relational structures. So, if I have a structure and I have some object in the index category, so I'm thinking of this n as being like it's the nth basic relation. The class of morphisms that I get by looking at all of the components of the natural transformations that represent A, that collection of all of those morphisms is the relation or the basic relation of A at the object n. So I would like to say that this is a sub-object of like what I've been saying all along, right? Like it would be like a subset of A choose 2 for graphs or a subset of A cubed for ternary relations. Unfortunately, I actually don't know if that's the case in general. The definition that I gave, I don't believe it immediately implies that it has to be the case. So in good cases, it is. But in general, I think all I can really say is this. But again, I'm not sure. It might be that it has to be a sub-object of that, and I haven't realized why. But we can still just define it to be that set of morphisms in general. And yeah, unfortunately, I do have to actually like iterate through all of the representatives, for the sub-object, but we can do that. There's a bunch of natural transformations. Oh, and I guess, okay, if you have an infinite amount, if you have not infinite, if you have a large amount of representatives, then this is a proper class, but let's not worry about it. So morphisms morphisms in the index category similarly give us those things that I called relators before between the relations. So you can have that too if you want. It doesn't really change anything too much. So if I have two structures, then I can now define a morphism from one to the other as a morphism in the original category C where the universes came from, where if I take the image of A under that, and by this H of A, I mean this image of row H composed with F for any representative F of the structure that I had in mind. So this definition guarantees that that exists. So if I bring A forward by using H, then if I have that that's a substructure of B, then I say that that's a morphism. And so this, is a large generalization of like a graph homomorphism, right? If I look at all the edges, I move them forward by H, then I should get edges that are in the codomain. And of course, this is as subobjects of row B. It's like the biggest structure, the biggest like total structure on that universe. And so there is actually a category of structures with that signature that has this as its definition of morphism. And so the proof isn't like extremely long, but it's also not entirely trivial. Like you do have to do a little bit of work to prove that morphisms can be composed with each other to yield other morphisms and that it's associative and so forth. Like it's not entirely trivial. So it's possible, I don't know for sure what the odds are that this is true, but it's possible that Bourbaki experienced some version of this when trying to determine how to come up with a categorical formulation, or like experience something that was reflected by that this is not trivial to show, and then just decided that it wasn't worth trying to set it up properly because like if you just try to do this with the signatures pre-signatures I defined before, you'll in general fail and it won't work. You won't have the nice structure. You won't even have a category. So that could be the reason that this was difficult to do. But okay, so now actually I think I've gone a little bit long. Should would we usually wrap up at 50, like 10 before, or what's reasonable here? Okay, well
Which one? I don't know. Go.
Okay, I don't want to take, I'm not going to take like 3 hours though. I'll try to
Okay, okay, it's fine.
okay.
Let's, are you an hour earlier?
Uh,
And anyways, so let's do this like an hour and 15 minutes. We started at 7:05, so 8:20. Is that good?
okay, yeah, I should definitely be good by then. I took a bit longer than I expected, but I appreciate all the great comments and questions.
Okay, good.
Um, thank you. So okay, so now I can tell you what finite structures are. So if we have a signature where the index category I is a finite category, finitely many objects and finitely many morphisms, and this source and target, the C and D, are both set, then I'm going to say that that's a finite signature when each of the like full relations, the row A of n, are finite. And so this is the thing that I was saying you would kind of expect to be like the overarching relation that like if I go back here, that like this was giving us a subobject of. Um, I'm more confident saying that that's the that's the case for these finite structures, but in the infinite case, or not even infinite, but just in general for things that are further away from set, I'm much less confident about making that assertion. So I believe that it's true in the set situation that I just described, but I'm not sure in general that this has to actually be a subobject of that thing. So it's a bit of a technicality, I guess. But okay, so at least in the set case, though, we really do have something which is just like the set of all possible unordered pairs or triples or subsets of our universe or whatever it is. And so I'm asking that all of those things be finite as well. So no taking the set with two elements to the free group, the set of elements of the free group on two elements, for instance. That's too much. Okay, so a finite structure is a structure that has a finite signature and its universe is a finite set. And so this definition then is broad enough to include, directed or undirected graphs, algebraic structures, provided that you view them as relational structures of the appropriate arities, topological, finite topological spaces or finite structures. So anything like that you'd care to look at, those are all finite structures. So I'm going to use this notation.
Can I just ask you, Bourbaki never intended to be anything finitistic about his structures, their structures.
Yeah.
But you're restricting to finite structures because you have some type of theorem about its relationship to Bourbaki, or what?
Yeah, because I want to talk about something that's a generalization of this Hilbert result on symmetric polynomials. And so because
Okay.
the variables are going to be like the things I did at the beginning where I made variables for each of the possible pieces of the structure, I need there to only be finitely many, or else I didn't want to do the whatever the infinite like power series analog of this was. So I just,
I understand. Okay, now I see it. Okay, good. Thank you.
yeah, of course. So I'm going to use this notation, structures of signature row on the set A. Now I'm thinking of an underlying set as opposed to a more general underlying object. Um, so I'm going to call that a kinship class. So it's like a similarity class, which would just be all the structures of the same signature, but the things that are even closer are kindred to each other. And so those would just be all the, for instance, like all of the graphs that have the same set of vertices, but their edge sets could potentially be different. I'm frequently going to need to talk about all of those objects together. So, well, as you might imagine, a substructure of a structure is just a subobject in the appropriate category of structures, in the usual categorical sense, which you can unravel into what it says about the various basic relations of the structure. And so, well, now I'll remind you what the situation was with that result of Hilbert. So, if I have a set of variables x, then the set of permutations of x acts on the group of permutations of x acts on those variables, and hence on the corresponding polynomial algebra over whatever commutative unital ring R that you would like, by swapping the variables with each other. And so the polynomials that are invariant under this are the symmetric polynomials, and they themselves are an R algebra for whatever ring you choose. And so a classical result of Hilbert is that there are certain very simple elementary symmetric polynomials which generate the algebra of all symmetric polynomials. And so I'm going to now describe a generalization of this for finite structures. And the Hilbert result will be the result for just like plain sets. Or if you want to, the index category is the trivial category. And both, C and D from the previous discussion are set. And the functor in question is just, we're just going to use the identity. Then that's it. So that will be the Hilbert result. So, well, just like I did in my examples before, I'm going to define a collection of variables for a given signature and a given underlying set. And well, what I'm going to do is basically just make a variable for each basic relation. I only had one before, so I didn't need this indexing. And then for each element of this extraction, this would be like the A choose 2 or the subsets of A or A cubed or whatever before. I just make a variable for each of those things. In other words, these are like what the xij were for the graph case or the xijk were for the ternary relation case. So I can make a set of all those variables. And then just like I defined that monomial for the graph case that checked for that specific triangle, if I want to, for any structure on that underlying set, I can make a monomial which is just the product of all of these variables that correspond to each of the little pieces. So I can make a monomial that's basically the one that checks to see if that specific structure is a substructure of whatever thing you have. So this is just like the x12, x23, x31 that I had in the graph example at the beginning. Well, I can make a polynomial algebra if I want by looking at the subalgebra of just all polynomials with some, ring coefficients in these variables, x row A. I can look at the subalgebra generated by these monomials that are like these sort of reasonable monomials checking for substructures. And so this is what I'm going to call whole row A R. So the polynomial algebra for that signature and that underlying set.
Are you making a distinction between capital Y and lowercase y?
Lowercase ya was supposed to be like a specific one of these things for the structure A, whereas this capital
Next slide. Next slide.
this
There.
capital Y row A is the set of all such monomials.
Okay.
Yeah, thanks. I guess I didn't mention that. So yeah, the set of all such monomials that you could create. And so, well, okay. I mean, maybe reading the definition won't do you really much good, but if you can imagine that permuting the names of the elements of your universe can permute these monomials, it can also act on the polynomials that are made from them. So in other words, it's just like if you swap around the vertices for your graph, then it will swap like the monomial that corresponds to a triangle over here to one that corresponds to a triangle over here. And so anything that is, permuting that underlying set will give us a corresponding permutation of these polynomials. And, you can extend it linearly, of course. And similarly to the classical case of the symmetric polynomials, we can say that a polynomial in here is symmetric when it's invariant under this action. And that's like the example I gave of a polynomial checking for how many triangles there were in a graph, because that quantity is something that's invariant under renaming the vertices of the graph, right? Even if you look at a different isomorphic copy of it, it'll still have the same number of triangles. They might be in different places, but you'll have the same number. And so that was an example of one of these symmetric polynomials. So, well, similarly, we can have a group acting on all of the structures of a given signature and a given underlying set by just looking at what that permutation of the underlying set is doing in terms of the relations for that set. So this would be like saying, well, if I have a permutation of A, that induces a permutation of A choose 2, and hence if I have any graph on the set of vertices A, then I can, of course, view that action as taking it to a corresponding graph where the vertices have been moved around. So that's all that this is saying. Given that action, we can look at the orbits of that action, and these would just be the classes of structures of that type on that underlying set that have that are isomorphic, right? That's acting as isomorphism, because that relabeling will be an isomorphism. And so we could look at all of the different isomorphism classes. And I can now use that to define the elementary symmetric polynomials in this generalized sense. So the elementary symmetric polynomial for an isomorphism class of structures, whether it's graphs or ternary relational things or, finite topological spaces or whatever, the elementary symmetric polynomial for that is just the sum of these monomials for all the different instances of that isomorphism class. And so, for instance, if you do this in the Hilbert case, your structures will just be subsets of the universe. And so an isomorphism class will just be a subset of a particular size, like say 3 things. And then this polynomial will just be the sum of all monomials that have three variables in them. Like say 3 distinct variables in them. And that's it. So then that is like, that is what the elementary symmetric polynomial is supposed to be. So If you do this for other types of structures, well, I mean, I gave you the example for graphs before. There would be a corresponding elementary symmetric polynomial for cliques of size 3 or for triangles. And what I wrote down in detail before is an example of this, where you take the isomorphism class to be corresponding to subgraphs that are complete graphs on 3 vertices. And so you can check, it's a calculation. You can check that the elementary symmetric polynomials are symmetric polynomials in the sense that I defined before. So at least this basic part of the invariant thing works here. So what I was able to show was actually that Hilbert's argument, I mean, it took some modification, but for the most part, it was the same argument. Hilbert's argument actually will generalize to this abstract setting. And so if you give me a symmetric polynomial, like the much more complicated one that I showed you for associativity for magmas, checking if it's a semigroup. If you take any symmetric polynomial, I didn't define the degrees or the weights, but there's some way of quantifying the complexity of these things that's natural. If you give me some symmetric polynomial, then there's going to be some polynomial where these z rho a are supposed to be stand-ins for the elementary symmetrics. There's some polynomial combination of the elementary symmetrics that makes the given symmetric polynomial. In other words, it is still the case in this more abstract setting that the elementary symmetric polynomials generate the algebra of all symmetric polynomials.
Right. In addition to generating, you have the sexual constraint generating a way with the weight at most d.
I'm sorry, what?
I'm saying, and not just generate, but you also have the weight at most d.
Yeah, so I didn't define what that was, but that's really the interesting part because as I mentioned at the beginning, there are sort of cheap ways of making a polynomial algebra that like checks, that you have a given property. What's really interesting and what I do in more detail in the preprint version of this that is a little more detailed than my thesis, the part of my thesis on this, you actually get control over how complicated or how big the substructures are that you have to look at when looking at these symmetric polynomials. Like, as you don't want to have to use all of them. If you had to use all of them, it's not really interesting because you'd have to check huge things. But you actually get some control where if you have a simpler positive formula that expresses your property, then you're able to translate that into a smaller collection of smaller order structures that you have to check in order to check the property. So yeah, so it's actually you actually get that control over the degree that is making it so that this would be kind of useless if you didn't have any control over it, or at least not as interesting. So I think I didn't expect to have time to give the details of that, but it is true that you get that control. So I'll just briefly outline the proof without defining the weight and everything. So it does follow Hilbert's result. So the first thing that we need is that you can actually factor these special monomials, the y, like ya or yai, where if you have a product of those monomials, you can actually rewrite it as a single monomial that's y indexed by the join of all of those guys in the lattice of substructures of whatever the biggest possible structure on your universe is, times some polynomial. And having that fact is important, that you can factor the product of monomials this way. And then you can induct on the size of the universe, which is like Hilbert's proof. So if you have it for A1 through AN minus 1, you want to stick on one more element and be able to do it there. You look at all of the variables that depend on AN, whatever that new thing that you're sticking into the universe is. So that's what this capital A sub n is all the variables that depend on that A sub n. And so if you restrict your polynomial to something where all of those variables are set to be 0, or your structure doesn't actually use that element in any way, then you get something that's a symmetric polynomial in the one smaller universe. And so by the inductive hypothesis, you have a polynomial in terms of the elementary symmetrics of weight at most d, so that this restriction is actually that polynomial evaluated on the elementary symmetrics. And so then you have to argue that replacing the monomials appearing in this G1 with the corresponding monomials where you stick in the one additional element in your universe gives you a new polynomial, which I'll just also call G1, so that if you add G1 and G2 together and evaluate on the elementary symmetrics, you get F, where this additional term is also a symmetric polynomial. So that's like a really brief summary of the proof. It does differ a little bit from Hilbert's argument, but it's essentially the same argument. And it turns out that it really didn't depend on having a discrete set of things that indexed your variables. Just any finite structure in the sense that I described before will work for this. I just wanted to put up a few references here. I always post my slides on my website as well. So if if you want to take a look, or look things up later, the preprint from this here is the thing that has a little more detail, and it describes how to turn a positive formula into one of these polynomials. And I mean, of course, this book is actually much older, but the version of the English translation that I used of the theory of sets was this 2004 one.
You just said that these that by your website is where one can find this.
Yeah, I can post my website in the chat. It's so it's just my last name .cool.
Okay, thank you.
Yeah, I couldn't get aten.com because it was the website of a Taiwanese manufacturing concern.
Yeah, anything.com with 4 letters is bound to be very expensive.
Yeah. Well, thank you all so much for
thank you. And any questions?
Yeah. Sorry, this is incredibly basic, but I'm looking for examples that I can wrap my head around of sort of structures that fit under this categorified definition that I might encounter in the wild that wouldn't have worked with the prior less generalized theorem.
Oh, like in the sense that right. So for the less generalized theorem, okay, sorry. So there's a more general version of the result of Hilbert, and what I just stated was the version where you just had the just all permutations acting on the underlying the set indexing the variables. But there's a more general statement that is if you just have some group that is acting on your variables, right? Is that what you're referring to?
Sorry, no, this is a really maybe I'm asking it poorly or something, but you generalized just maybe I'm just totally not understanding what happened. You generalized a classical result as by generalizing the structure it operated on and then generalizing the result to operate on the structure.
Yeah.
And so in this generalized structure, right, the old result could handle certain types of things that we would consider structures. The new result handles a more general class of things as structures, like categorified structures. So what are some examples, or am I just missing something?
I mean, like, so the original result of Hilbert was like, if you're going to think of that as being in reference to structures,
Yes.
the structure in question would just be a structure on a set would just be a subset of that set, like just in general. And
Right.
so yeah, I mean, you could imagine that, you have like, if I want to look at unordered pairs, say like graphs on a given set, that is a subset of the set of all possible ordered pairs, right? But I don't want the action that is just any permutation of the ordered pairs. I only want to allow the permutations that are induced by relabeling the vertices, by permuting the vertices. So
Okay.
that's a different action than if you did the like, the Hilbert style action on it, it doesn't respect the structure of it at all. It's just forgetting that it came from being A choose two, and it's just treating it as like it's a new set. And so that doesn't preserve the graph structure in any way. So you wouldn't expect that I mean, you don't get something that would tell you anything about counting things or about, yeah, its substructures.
Oh, okay, I see what you're saying. Sorry, I think what happened was I didn't quite realize how limited what you generalized was in terms of it's more about the things you're able to say are much richer. I guess my other question at a very high level, and this is again, I'm not quite sure if I'm even asking this right, is does this give us then a like there's like a lot of stuff with generating polynomials. Does this give us a general sort of way to describe like where generating polynomials come from?
So I actually haven't thought about I actually haven't thought about like what the relationship that this has with generating functions is.
Hmm.
Um, but I would be curious to find out. I mean, I've been pulled away by other things in the meantime, but yeah, that's something that I would definitely be interested in understanding, like what the relationship is there. I think I do mention in the preprint, but not in my thesis, that at some point John Baez pointed out to me that okay, now I'm spacing on who it was, even though it's a familiar name. Somebody had a paper on operations with structures that was more related to like the generating function viewpoint. It was actually like back in the 70s, I think, and it's not this like categorical notion. It's more close to like the model theory one, but it was something in a similar vein with counting the number of examples of or counting the number of structures of a certain type and doing that behaved with doing operations with them. Um, you can find it in the preprint that I linked here. I just can't remember now who it was, but I think it's called Operations with Structures. And so that was a similar thing that you might find interesting.
Okay, thank you. Appreciate it.
Yeah.
I just want to say, look to your website. It looks good. I'm going to have to read this because it, you know, look forward to reading this, and I can then forward you also that uh, part of McLean's biography that I mentioned earlier.
Oh yeah, please do. That sounds great.
Hmm.
Yeah,
Yeah, thank you.
yes,
Any
and
other
I will.
questions? Anyways, let's thank the speaker
I'll
again.
have I'll have to read your paper more carefully before I have any more questions. But
Sure.
thank you again.
I'm
Thank
looking
you.
forward to it. Thank you.
Thank you. Okay, thank you. Thank you, Charlotte. Thank you, everybody. Next week we have our last talk of the season, and we have Matt Cushman is speaking about something cohomology, something. Um, you're all welcome to join us then. And anyways, again, Charlotte, thank you very much. Have a
Yeah,
wonderful
thanks again
evening.
for having me.
Okay, take care. Take care, everyone. Good